Hi guys, today we're discussing chapter 10 or chapter 9 depending on the stream you are in, and the chapter is on the transfer of thermal energy. Now, in this chapter we'll be discussing the three modes in which thermal energy can be transferred, and they are conduction, convection and radiation. After which we'll discuss some of the applications of each of them, so we'll explore each application after we have finished covering each of the mode of transfer of thermal energy. Now, before we talk about all the modes of transfer, we talk about the transfer of thermal energy itself. Now, transfer of thermal energy occurs only when there is a temperature difference. Alright, and it can only and the flow of thermal energy flows from the region where there's a higher temperature to the lower temperature. So if you got 100 degrees and 30 degrees object in thermal contact, what does thermal contact mean? Basically, they are in contact in such a way that thermal energy can be transferred. So when you have two objects of different temperatures in thermal contact, the flow will occur, or the flow of thermal energy will occur from the region of the higher temperature to the lower temperature. So from the 100 degrees Celsius object down towards the 30 degrees Celsius object. Now, eventually after some time, once the thermal energy has been transferred, both of objects will reach the same temperature, and then we say that there's actually no net flow of thermal energy between the two objects. Why the word net? It is because actually there is still flow between the objects. So object A 65 degrees, object B 65 degrees, they are both in thermal contact. There will be a flow of thermal energy from A towards B. In turn, there is also a flow of thermal energy from B to A. It is just that these two numbers are the same. That's why the net effect is that there is no flow of thermal energy. So again, flow of thermal or net flow of thermal energy can only occur with a difference in temperature, and it flows from high to low. Now throughout this discussion, you will see me the part of the notes that will be highlighted. These will be the parts that will be important, and you will need to memorize all of this. Alright, so now we'll go into our first mode of thermal energy transfer, which is conduction. Now, what exactly is conduction? Now, conduction is just the flow or transfer of thermal energy through a medium without actually any of the medium moving along with it. So how exactly it works, we can summarize it succinctly in two words, which is molecular collisions. Now you can use a lot of fancy descriptions or use a lot of description to describe, but the main point is that because of the collisions between the molecules that make up the object, thermal energy is transferred. Now, before we go into this discussion, you need to do a little bit of recalling from your kinetic model of matter, which states that the higher the temperature of an object, the higher the kinetic energy of the molecules that make up the object, and hence the higher the velocity of the object, of the molecules that make up the object. So imagine these are the molecules or the atoms that make up an object, and I have a heat supply somewhere here. So this fella here will gain or be higher temperature, because this part of the object here is at higher temperature. The molecules will start to vibrate a little faster. Because it is vibrating a little bit faster, it will knock into the next fella, and this fella will in turn gain energy. And because this fella now is already vibrating a little bit faster, then he will knock into the next fella, and this molecule will now start to vibrate faster. Eventually, all the molecules will start to vibrate faster. They have a higher gain. They are moving faster. The kinetic energy of the molecules are faster. That's why, as a whole, the object has a higher temperature. Now, again, it's in green. You can choose to describe it like that, but the basic concept is that thermal energy transfer for conduction occurs because of molecular collisions. Now, another point of interest to discuss is the states of matter. Which state of matter, of which you need to know three: solid, liquid, and gases. Which ones are the best conductors of thermal energy? Solids are far better conductors than liquid and gases. Now, why? We fall back to our kinetic model of matter and how the particles are arranged in solids, liquid, and gases. So in solids, the particles or the atoms are arranged very closely, liquids slightly further apart, and gases very, very far apart. Because solids are so close together, when the left side gets heated up, it gains kinetic energy, and it can quickly transfer the thermal energy or the kinetic energy to the next molecule. Liquids will be slightly more difficult because it's slightly further away, so you got to vibrate a little bit more or move a little bit more and hit. Gases, it's very, very difficult for it to transfer the thermal energy to the fellow because of the space in between the molecules or the atoms. So in solids, the kinetic energy can be transferred more quickly. That's why conduction happens best in solids, followed by liquids, followed by gases. Now, above and beyond all of that, there is another type of material that you do need to know, and that is metals. Metals are by far the best conductor. Even in we discussing solid, liquid, and gases, are by far the best conductors of all the materials. Why? It is the same reason as to why metals are good conductors of electricity. It is because of the presence of free electrons in metals. Now, in most objects, the atoms is made out of the nucleus, and you have the electrons orbiting around it. And these electrons are fixed to this nucleus. So they are fixed in the position in the atom, and it can only rotate about here. But in metals, alright, the atoms can actually, the electrons can actually flit around from one molecule to the other molecule to the other molecule and transfer. So because of the presence of these free electrons, thermal energy can now be transferred more on top of molecular collision, number one. It can also transfer via the process of something called free electron diffusion, because the electrons at the portion where the object is being heated up, because it is not bound strictly to this one atom, it can just immediately shoot all the way to the other side and transfer energy to this atom. It doesn't have to slowly wait for this guy to transfer to this guy to transfer to this guy. Because it's not bound, it can immediately just go all the way. So metals are the best conductors because of these two reasons. On top of the normal way of molecular collision, we call the process where the electrons gain energy and quickly transfer energy to the other side as free electron diffusion. Alright, so just a quick question. Do liquids conduct thermal energy? Yes, solid, liquid, gases all can conduct, but liquids conduct thermal energy very slowly. Gases even worse than that. Alright, so you can do this example in the lab. You have water, and you have something that's holding on the ice to the base of the beaker or a boiling tube. You heat up only the top portion, you will realize that the top portion here will start boiling, but the ice still hasn't melted. Why? Because liquids in general are not good transfer of thermal energy via conduction. So that's why we call them poor conductors. And because of that, they cannot transfer the thermal energy fast enough to melt the ice, but the water can boil at the top already. Alright, so another way we term poor conductors, another term we use to describe poor conductors is insulators. So poor conductors are called good insulators. So what are some examples of materials that you know of that are good insulators? Polystyrene, wool, fiberglass. All of these materials, they seem solid to you, but actually they are good insulators because they have a lot of pockets of air inside. And because air is a good insulator of thermal energy, or poor conductor of thermal energy, therefore these objects are also poor conductors, and we can see them in some of the applications. So just to summarize, best conductors are metal, solid, followed by liquid, followed by gases. Poor conductors are also called insulators. Right, and we will explore some of the applications. Now, actually the next slide is already talking about convection, but I would rather ask you to now just flip over to 10.5, and I would like to discuss about the applications of conduction very, very quickly. So can you flip over to 10.5 over on this slide? Alright, so applications of thermal energy transfer, conduction. So there are a lot of situations in which we need objects to be a good conductor. We need objects to be a good conductor because we want the thermal energy to be quickly transferred. And when we want it to be quickly transferred, we use the best conductor that we know of, which is metal. So some examples of application, you want your pot and pans to heat up quickly, so that's why in general they are made of metals. Soldering iron, you want this is soldering iron. You want the tip to be hot enough for you to solder things on your electrical components. You don't want to be made out of plastic, and then it will take so long for it to heat up, all right, for you to even begin soldering. Car radiators, solar water heaters, heat sinks in computers and TVs, all of these are made out of metals. In fact, I can show you a little bit. If you can see behind my CPU cooler, you can see a lot of those lines there. Those are actually metal fins. So they draw out thermal energy quickly from your CPU. And then the fan blows away the hot air towards the back of your PC. Alright, your GPU also, your graphics card also have all these metallic parts. Alright, these are all heat sinks because the heat is sunk into these objects or drawn away from these objects. Alright, because of that, then the thermal energy can then be transferred very quickly away from the parts that are heating up. Alright, so apart from good conductors, you also want applications where you have poor conductors or good insulators. So in applications where you need the energy to be, or thermal energy to be transmitted very, very slowly, we use things that have a lot of air in them. So the portions of the cooking utensils that you need to touch, you of course don't want it to be as hot as the metallic parts where you're cooking. So that's why we use wooden or plastic handles. Oven mitts, they have a lot of trapped air inside. That's why you can hold on to the hot pot without burning your hand. Double glazed windows, alright, not in Singapore but in countries where you experience winter. The windows are made out of actually two panes. In between is actually air. So the air cannot move. Air is a poor conductor of thermal energy, so thermal energy cannot transfer through or transfers very slowly from the inside of the house to the outside, so you don't lose the thermal energy. Winter jackets also work the same way. You use duck feathers, you use wool, or use feather. The reason is not because those objects are good insulators, because those objects trap air. So that's why when you have winter jackets, the puffier it is, the warmer you feel during winter. Alright, so we'll discuss about convection next. Alright, we are now on 10.3, convection. So convection is basically the transfer, it's the second mode of transfer of thermal energy, and it's the transfer of thermal energy via convection currents, which is formed due to the differences in density. And it can only happen in a fluid, which means things that flow, liquid or gas. It does not occur in solids. Alright, so what is the difference? In conduction, thermal energy is transferred because of the word, I hope you can remember, molecular collisions. For metal, you have another additional way, which is free electron diffusion. But in convection, the particles actually, or the molecules actually move along with it and transfer the energy. So because in solids, your molecules are fixed in space, because it can only vibrate about fixed position, convection cannot happen in solids. Alright, so what is convection? So I know you all know already, it's hot air rise, cold air sinks, but you are now taking the O's, so you need to explain a little bit more. So when you have an object being heated up, a fluid being heated up, something that flows being heated up, the portion near the flame gets heated up, it will expand. Because it expands, it becomes less dense. Why? Density equals to mass over volume. When volume increases, I divide by a bigger number in the denominator, I expect the density to decrease. Alright, you do not have to use this for explanation, just for your understanding. Expands, less dense, rises. The upper region, which is cooler, is comparatively denser and sinks. So I know you always used to say hot air rises, cold air sinks. Now we need to include the explanation on density and expansion. Alright, and because hot air rises, because it is less dense than cool, which is denser and sinks, you have a convection current set up. So the hot air will rise, the cool air will sink, the cool air gets heated up, the cool air becomes less dense, rises, and it repeats until the whole fluid becomes of the same temperature. Alright, this is what the explanation will be for in cases where we are heating. For cooling, it can also happen very simply, same explanation. When you cool something, it contracts. Because it contracts, it becomes more dense and it will sink. The surrounding air, which is warmer compared to the air that is cool, is comparatively less dense, and then it rises. And therefore, I set up a convection current which transfers thermal energy. Alright, so an example of how convection is vital or important is the formation of land and sea breezes. Alright, in the day, the land gets heated up very much quicker compared to the sea. Alright, because of this, it is much hotter over the land. Hotter, expands, less dense, rises. So now you have a space where suddenly you have a lack of air. So the cooler air from the sea will then move in, and then you get your basically what is called your sea breeze or wind coming from the sea. Alright, and the convection current is set up. At night, the land will quickly lose all its thermal energy, so the sea will be warmer than the land. Because the sea is warmer, the air above the sea comparatively is warmer, it is less dense, it rises, and then the cooler air from the land will then rush in, and therefore you have a land breeze being formed. Alright, so let's talk about some applications of convection. Alright, again flip over to 10.5. I'll skip past radiation. Alright, just after the portion on conductors, we talk about some applications of convection. Alright, convection is important. We use it every time, all the time. Refrigerators, you use it for your AC or your air cons. Alright, but the explanation still remains the same. You start off with what is the application. Is it a cooling or is it a heating kind of application? If it's a cooling, then you start with cooler, contracts, denser, sink. Warmer, less dense, rises. Therefore, convection current set up, which then cools the whole refrigerator. Now, something to note of, that's why we always have our AC units or our fridge cooling units always near the top. It is so that we can form effective convection current. Imagine you have a cooling unit that is placed at the bottom of the object you want to cool. So, cooler, more dense, sink. So, only the area here will be cool because it continues to sink. The warm air continues to remain at the top. So for it to cool effectively, you always put a cooling unit near the top. So that's why your ACs are usually found at the top of the room. Your fridge units are always found at the top of the room. Which then brings me for applications of convection. For heaters, in Singapore, not so common, but if you are interested in fishes or you have a fish tank, then usually if you have an aquarium heater, you usually place it near the bottom. Why? You usually place it near the bottom because you want the heater to warm the air, expands, less dense, rises. And because of that, the cooler, denser water will sink, take its place, get heated up and rises, and it forms a convection current. Alright, the same argument applies if I put a heating unit near the top of the object that I want to heat up, then only the hot water will remain at the top. The cooler water will always remain at the bottom. So you won't have an effective convection current being formed. Alright, finally we come to our last portion, which is radiation. Radiation is possibly the easiest to understand but the most difficult in terms of application. Alright, so what is this radiation mode of transfer of thermal energy? Radiation is the transfer of thermal energy in the form of an electromagnetic wave. I know we haven't covered this yet, but you will soon. And this electromagnetic wave is called infrared radiation. Now, I must stress this because a lot of students will tend to use the word thermal energy. So I would say that when we're talking about radiation, I would suggest that, or strongly remind you that you need to use the term infrared radiation. Now, infrared radiation does not require a medium. In fact, that is how the earth gets warmed by the sun. Alright, radiation is affected by quite a few things. You have to remember one of them, all of them. Color and texture is possibly the most tested one, so you need to get good at this. Alright, we'll explore this all a little bit later. Surface area and surface temperature all will affect the rate of radiation of an object. Alright, so what do we know about color and texture on the emission? That means being given out, the infrared radiation that is being given out. So you notice that if we talk about color and texture, texture is whether it's rough or smooth. So we use it as dull or shiny as opposed to shiny. Color, we always talk about it in terms of black or silver. Right, so if you do an experiment where you have two objects, same temperature, you have a sensor, the only difference is that one is black and dull, the other one is shiny and silver, you will notice that the black tin cools down much quicker than the shiny tin. And why is that so? So from there we can make our own deduction that black dull surfaces are good emitters, or sometimes we use the word radiators. That means they give out infrared radiation much better than shiny silver surfaces. Alright, a common mistake that students always make, they say black and dull are better emitters of thermal energy, and then or black and dull surfaces are good emitters or radiators of heat. And it is wrong, because it is not thermal energy or heat that is being given out, it's just infrared radiation. So do not use this term. I will say again and stress upon this, you must use the term infrared radiation. Alright, if I have a heating object, temperature sensor, and two objects here, one is black and dull, one is shiny and silver, I have a heater here, you will notice that the object that is black will have a tendency to have the temperature increase that is much faster than the shiny surfaces, which means we know that now, or we can make the inference that black dull surfaces are better absorbers, again not of heat, not of thermal energy, but infrared radiation. So black and dull compared to shiny are good absorbers of infrared radiation. So these are the few terms that you will need to memorize, and I already highlighted this. Dull black surfaces are good emitters or radiators of infrared radiation, but at the same time they are also good absorbers. So they emit well infrared radiation, but they also absorb infrared radiation well. Shiny and silver surfaces are poor emitters, means they give out infrared radiation very slowly, and they also absorb them very slowly, infrared radiation. When I say an object is a poor absorber of infrared radiation, imagine it's a shiny surface here, it doesn't absorb well, it means it is a good reflector. So you can either say poor absorber or good reflector. Alright, so color and texture will affect the rate of infrared radiation, and based on the application we want, we will explore this a little bit in a few minutes time. We will want certain objects to be dull and black, we want certain objects to be shiny and silver. Alright, so other factors affecting emission and absorption rates of infrared radiation. Alright, if you have two objects exactly identical mass and material, except that one object has a much larger surface area, it will then have a tendency to emit or absorb infrared radiation at a higher rate. This one is quite logical. I have an object here, small, as opposed to a same object, I flatten it out. Then of course this one is gonna have much more surface area to radiate out the infrared radiation. It also has that much more surface area for it to absorb infrared radiation. That's why they are, in general, the larger the surface area, the better emitter it is, the better absorber it is of, again, infrared radiation, not TE, thermal energy, and not heat. It is infrared radiation. Alright, what are some other factors? Surface temperature. The higher the temperature of the object, the higher the rate of emission of infrared radiation. Of course, again, same thing. Imagine if I'm standing here, I got two objects, exactly same mass, same material. Say that one object is at 15 degrees Celsius and another object is at 1500 degrees Celsius. You will feel the heat coming towards you more from this fella. So, and the reason why you feel the heat on your face is because actually it's radiating a lot more infrared radiation compared to the 15 degrees Celsius by due or virtue of its higher temperature. Alright, so these are relationships that you need to remember. So some examples: solar collector. A solar collector is basically just if you look at the top view, an object with a copper pipe in the center. Alright, so what it does is that usually we will want it to be a blackened surface, so that when infrared radiation from the sun comes, I want it to be black and dull, because black and dull surfaces are good absorbers of infrared radiation. Because they are good absorbers, then my solar collector will then heat up very quickly, and then it can then heat up the water inside the water tank. Alright, okay, you can go through the solutions of this by yourself. Alright, let's talk about some applications of radiation. Alright, we're back now with the applications just after convection. We're going to talk about applications of transfer thermal energy for radiation. Now, we have all heard about the term greenhouse effect, but what exactly it is? We know that it contributes to the rapid warming of the earth, right? The effect is named after the effect seen in greenhouses, where infrared radiation from the sun can enter the glass roof. Then some of the infrared radiation is absorbed by the plants, and because it is absorbed by the plants, there is it changes to an infrared radiation of longer wavelength, but you can think of it basically as the infrared radiation has lost some energy because some of it is absorbed by the plants, and because of that it now does not have enough energy to go back out through the way it came in. So thermal energy via infrared radiation can go in, get absorbed, the remaining cannot escape and get stuck in here, causing rapid increase in temperature in the greenhouse. So farmers use this to keep their crops warm in winter. Alright, but on Earth, infrared radiation from the sun again can come in, but because of greenhouse gases that form a layer around the atmosphere of the around the Earth, some of it is absorbed. It now doesn't have enough energy to go back out, so it is reflected back in, which results in an increase in temperature of the Earth. Right? In terms of radiation, I don't strictly have examples, but it is useful or important for you to know how to deal with descriptions of color and texture for solving any application question involving radiation. Now, you cannot quote for me, for example, dull black and black surfaces are good radiators and also good absorbers of infrared radiation, right? But you cannot tell me both. You can only tell me one of them. Either you tell me dull black surfaces are good radiators of infrared radiation, or dull blacks and black surfaces are good absorbers of infrared radiation. Now, why this is so, or when do you use one over the other, depends on the application that you have. So recall the very first thing we learned in the chapter is that thermal energy flows from hot to cold. So your job first is to identify flow. So given an application, you identify which part is hot, which part is cold, then you draw the flow of thermal energy. Because thermal energy has a tendency to transfer from hot to cold, I draw the arrow as such. Now, identifying then the application. Do you want the container to remain hot for a long time, or do you want the container to cool down very quickly? So, for example, you want it to cool down very quickly. This is the case for your CPU. Alright, your CPU heat sinks, they heat up very quickly. So I want it then to quickly, it becomes very hot compared to the outside temperature. And I want it to quickly radiate out the thermal energy via infrared radiation. And because of that, then I want it to be dull black, because dull black surfaces are good emitters or good radiators of infrared radiation. I cannot use good absorbers because it doesn't apply here. So what if I want the inside here to remain as hot for as long as possible? So for example, like your flask that you keep your coffee in, you want it to remain as hot for as long as possible. Then your reason should be you want the heat to go back into the surface or into the container and not out and lose thermal energy via infrared radiation. So in that sense, I want the surface of this container to be shiny and silver, because shiny and silver are poor emitters of infrared radiation. Then as such, because they reflect back the heat, back into the container, then your container will continue to remain hot for a long time. So select color and texture, followed by explain the reason why you choose the color and texture, because it's a poor emitter, good absorber, good emitter, depending on the color and texture. Now, common questions that appear as a whole. Hot is a favorite that in recent times it hasn't appeared quite some time. Vacuum flask. Alright, vacuum flask has a whole load of features that prevent or slow down the transfer or loss of thermal energy. Alright, you have the plastic stopper at the top. Plastic, because it's a good insulator, it prevents thermal energy loss via conduction. Alright, the vacuum flask has a layer of vacuum here. Right, the layer of vacuum will prevent any transfer of thermal energy via conduction and convection, because convection cannot happen because it cannot flow. The physical flow is stopped, and conduction cannot occur because basically there's no particles in a vacuum to help you transfer the energy out from the flask to the outside, from the outside to the flask. So that's why things that are hot will remain hot, things that are cold will remain cold inside. Alright, but of course you need to have spaces to hold up the flask itself in the container, right? So that's why we use cork. Cork is a good insulator because it has a lot of trapped air inside, and air is a good insulator of thermal energy. Alright, silver surfaces of the vacuum flask also prevent any thermal energy transfer, because shiny silver surfaces are poor emitters of infrared radiation. Therefore, thermal energy from the inside cannot go out because they are poor emitters of infrared radiation, so it will remain hot. Alright, one last example. So the radiators of a fin of a car are designed to carry heat away from the hot engine. They are usually made of hollow metal pieces through which fluid flows. They are also black. Explain how the features of the radiator fin helps in increasing the rate of thermal energy transfer. Alright, so these are all the explanation. You have thin fins because you, instead of having a block, you have all these fins instead, like in the CPU that I showed you just now. Because of that, it increases surface area, so it increases the rate of thermal energy transfer by radiation, so it will cool down very quickly. There's more surface area for which radiation can occur. Metal, because metal are the best conductors, therefore it can transfer energy quickly from the hot part to the cooler parts to the metal. Radiator fins are black because the fins will heat up. You want it to be a good emitter of infrared radiation. Alright, so all these features use the convection, conduction, and radiation, the principles, to help it cool down an object very, very quickly. Alright, you can go through the example here at the back yourself. So just a quick summary. Conduction is via molecular collisions. Conduction happens best in metals. Then in the states of matter is solid, liquid, followed by gases. Alright, metals have the additional part on top of molecular collision. It has free electron diffusion. Convection, on top of saying hot air rise, cold air sink, it happens only in fluids. It cannot happen in the solid. Alright, so you need to talk also about the density changes. So become less dense, rises, denser sinks. And radiation, the important part, there are three components, that are three factors that affect it: color, texture, surface area, and surface temperature. So all of these you need to remember. Alright.